Hi, everyone. My name is Nishant Acharya, and I'll be presenting my work towards quantifying the impact of IXP shutdowns. This work was done in tandem with Vasilis and Amrish. So, why do we need to measure the impact of an IXP shutdown? Seems like a very weird question. A lot of people have done IXP centrality work. IXPs play a key role in reducing the cost of interconnections, and given the frequency and intensity of recent internet shutdowns, as can be seen from the images related to the 2024 Bangladesh shutdown and the Hurricane Maria shutdown, we can see that IXPs play an important role in determining the connectivity standards. In this work, we aim to quantify and identify regional IXPs that have the highest impact on the end user when it goes down. For example, if an IXP partially or fully is impacted, how much will the latency go up to reach the other parts of the internet? In this work, for now, particularly, we're focusing on IXVR Sao Paulo. It was chosen due to the size of the IXP facility, the location in an underanalyzed region, and the fact that there were two other IXPs, slightly smaller IXPs, that were nearby to see the cascading effect of an IXP going down. So before I move forward, I want to highlight the challenges related to this problem. In particular, we were able to highlight three challenges overall. The first challenge being the incompleteness around passive data surrounding IXPs. As you can see, existing passive data sources like ACE relationships, PRDB, and others are not complete, and as such cannot be used in isolation to identify internet topologies. This requires inferential methodologies or straight up ground truth data about the IXP member information, traffic, and other information overall. The second challenge is the low visibility of IXP network fabrics. IXP networks don't often show up on BGP forwarding paths, and trace routes to them might not overall return a reply through when you do an ICMP probe, which leads to challenges if you're trying to find out the overall traffic, the connectivity, or the inclusion in certain IXPs or exclusion of certain links in these IXPs. The third and the main challenge for this problem is the scalability of discovering AS level topologies. And the general idea is that brute forcing does not work. To give you guys an example, our target in this case, IXPR Sao Paulo, has approximately 6 million links. And to discover them via brute force, in which case is active measurement, is non-trivial, which highlights the need for inferential methodologies. So moving forward, I want to highlight how we address the challenge and the insights we used. The first challenge we tackle is the incompleteness around passive data, and out of which our first insight was to use data sources that report directly from the IXP. In this case, we use IXPDB. IXPDB automatically collects data directly from the IXP management system in order to provide an accurate and up-to-date view of the global internet connection landscape, which essentially means that you'll get the most up-to-date information. But sometimes it is lagging, in which case we use the IXP's own website to use the most up-to-date information in that regard. And as you can see, the difference between the member information and the IXPDB information, while not stark, we do have differences and we get more information using IXPDB. The second insight here is to merge the existing data sources to best cover the partial data. Existing data sources, while incomplete, can still give a partial view of the topology landscape. So in this case, we merge the known IXP links, information from historical RIPE Atlas trace routes, and the ACE relationship data from KAIDA. The second challenge we aim to address is the low visibility of IXP network fabric. The main idea is that we want to identify the inclusion of IXP links, we want to get the traffic to them, we want to get the path information, but IXPs just might not show up or might not reply. To address that, we use non-IXP links in the same city, and the idea here being that the traffic profile should not change by that much. The third challenge, as I mentioned, is the scalability of discovering AS level topologies. And there's a three-point approach to this. The first approach is to use inferential methodologies. Mainly, we use meta-AS critic introduced by Lokman and others. The central idea behind meta-AS critic is that ASCs are operated by businesses, and links between ASCs are a business decision. And similar businesses in a similar geological or geographical location have a higher probability of making similar business decisions. So through this process, we were able to identify links without relying overtly on active measurement. The second idea is also closely related to meta-AS critic. The idea was that while it is true that we might not be able to identifying a lot of links by doing active measurements in the same city or same IXP. It is also possible that we can utilize close by links. In this case, our exact range was double the size of the city. Sao Paulo is approximately 50 kilometers in radius. So we choose a radius of 50 kilometers to 100 kilometers to identify links. The idea here, the inference here, or the insight here is that these links are in the same geographical region. Hence, they might portray or they might show a similar behavior at the target IXP2. And the third one is to manually identify other IXP links in the region. Essentially, our goal here is to make sure to find out if there are any other pathways available. And if there are other IXPs available where near our target IXP, it is important for us to identify these links so that we can identify all other non-target IXP paths. As you can see in the table, though, it highlights the overall number of links that were discovered. The first row shows the historical traces we found out, which were not a huge number of 1,048. Using just inferential methodologies that includes the known links, known existing links, known non-links, which is we know for a fact this link does not exist. And then there is a set of probable links with the scores of 25% probability, 50% probability, and a 75% probability, which the number just jumped up. And then there is the known IXP links from, I believe in this case, is Decix and Equinix of 13,110, which leads to a huge percentage increase. Though the overall number of links we discovered is still low here. I believe approximately 14.55% of links were discovered out of the total number of links. So moving on to some results and analysis. The first thing I want to show you guys is the topology. Now, the graph here shows a 30% of the overall links. We were able to discover more of that. It's just I wasn't able to put the entire graph without just it making no sense at all. Overall, this is 30% of the links that we were able to discover, 30% of our total topology graph. The confidence links, as shown, goes from gray to orange. I understand it's not fully visible here. Apologies for that. But as I said, our confidence scores for known or discovered links go from 0.25 to 1, with a 0 being a non-link, which we don't show over here. The main takeaways that I want you guys to take away from that particular graph is, first of all, we were able to increase the number of labeled links, label including known links and known non-links, and also probable links by a huge margin. The second thing was that this is the scale of this task. As I said, approximately 6 million IPs for IXP or Sao Paulo. While some IXPs are not as huge, we want to make it generalizable. Hence, the scale of this task is quite big. The second thing we wanted to identify was the path increase inference. Essentially, we want to identify if an IXP fully or partially goes down, what would be the effect on the path length overall. So for this, we analyze multiple failure scenarios, partially due to the fuzziness of the process related to the inference. We take into account a 100% failure scenario, we take into account a 90% failure scenario, a 50% failure scenario, and a 10% failure scenario. For all scenarios that are less than 100%, again, because of the partiality of the information, we run 1,000 simulations. We run a simulation of 1,000 iterations, and each iteration removes random ASCs and links associated with those ASCs, and then we calculate the path increase. The step 3 here shows when a path will increase. As it says, a path increase is only recorded for known non-links and probable non-links. The idea here being that if an AS is known to not have a link other than that IXP, by definition, if that part of the IXP goes down, the path has to go up by 1, at least in the region. A path increase is only done for a link. Some definitions here. A link is existing if we can observe it in existing data being trace routes. A link is non-existing if we can see a consistent non-direct link between two ASCs. A non-direct link here is non-target IXP-based link. In this case, we are mainly looking for transit ASCs. And to get the probable links, we utilize certain parameters like the customer core, traffic information, number of IP4IP, and peering policy. We essentially compare the 1048 links that we initially found, and then we compare other ASCs with these ASCs and see if we can get a probability of how likely a link will exist or a non-link will exist. And here's some information regarding the path increase probabilities. The graph shows the proportion of known failures, or in this case, path increase, for probable and confirmed non-links. The 0.0 relates to confirmed non-links, and the others respectively are probable values. We see a proportional decrease over 1,000 simulations, which shows the evenness of the experiments. And as you can see over here, there's a disproportionate decrease from 90% to 50%, showing that the discovery of links might be biased towards particular ASCs through a process. And also, overall, we were on as much information as we were able to find. We found that 12% of the data was, or 12% of the overall ASCs were showing a path increase. The third thing that we want to figure out is the cascading effect on nearby IXPs. So when an IXP fully or partially fails, it can have a cascading effect on other IXPs. In this case, there are two other IXP facilities in Sao Paulo, DECIX and EdgeIX. We found a total of 13,1110 AS pairs or links that overlap with the other two IXPs. In this case, we're only considering the AS pairs with open peering policies. And for these, we find AS links for which the above would be the only non-IXPR link. For example, if the nearby IXP did not exist, technically it would be classified as a non-link. And we check based on that how much traffic would be diverted using peering DB statistics. Understandably, that is, as I mentioned, not a full data source, but that is the only data source we have without launching large-scale measurements. This graph shows the CDF of the amount of traffic from IXPR to the other two IXPs in case of a partial failure. The x-axis shows the factor of maximum divertible traffic. Maximum divertible traffic is defined as current link capacity, which is the IXPR's capacity for that particular link, divided by the new link capacity, which would be the capacity at DECIX Sao Paulo or Equinix Sao Paulo. The above graph shows that on average, the amount of load on the new link would be approximately twice the load it can handle, assuming max traffic and max link capacity, which means that these numbers can be fuzzied up and down depending on a real world scenario. Also, there are some links that definitely cannot handle the data being transferred to the nearby IXP links in any scenario, leading to congestion, as can be seen by the divertible traffic factor reaching over 100 for some. And as I mentioned over here, these are the takeaways as I just mentioned. Now, finally, I also want to discuss the limitations and ongoing work. But as I mentioned, our work revolves around a lot of inferential methodologies, and it is important to identify and highlight where things can be going wrong or where things can be improved. The first thing is that we rely on inferential methodologies, which are inherently fuzzy and ideally can use a bit more refinement overall. For example, we are using a simplified version of Metacritic to make things scalable, but that also means that our overall assessment is not entirely complete, as seen by only a 14.55% completion rate of the entire IXP topology around the IXP. The second point here is that we utilize data sources that are partial. As you have seen, we already utilize peering DB AS relations and others that are not complete, and ideally we can use some more refinement. The third part here is we are currently only utilizing traceroute data for active link detection. And we do plan on incorporating BGP updates to further enrich the data in the future. And finally, we utilize a set of features to compare similarity, as I mentioned in the previous slides. And it is not a complete set. So the overall list of features can be expanded upon for a more accurate and detailed similarity score comparison. And that is it for my presentation. I'll take any questions.
Thank you, Nishant, especially joining at a very late hour of your time. Do we have questions here in the room? Marino?
Not really a question, or maybe a question and a suggestion. Have you done some kind of validation of the results? And it would be nice to get in touch with the operators in the IXBR to validate some of the inferences.
No, that's a good suggestion. We haven't had the time to exactly validate our results. I believe Vasilis and I were talking about validating the ASLink discovery at least in the coming few weeks, but I will try to get in touch with the IXPR people to validate these results.
Yeah, and we have Pedro here in the room. It's a pity you're not here, Nishant, because Pedro is very well connected to the people in Brazil for validation. So actually, his next talk is going to be a lot about the data that he collected from DigBR and the IXP. Ignacio.
Yeah, thank you for the cool presentation. Similar to the question of Marino, I was thinking can you validate against a natural experiment? There have been a few cases, there have been a lot of cases where there have been IXP outages, some of them quite prominent. And I do recall even a few papers looking at traffic diversion from, I think it was London to, so maybe those would be useful cases to compare. I was also wondering whether you are including private network interconnections in your data.
Can you repeat the last line? I wasn't able to catch that.
So whether the data that you are collecting to see the impact includes private network interconnections, if you're trying to infer them somehow, or you're only looking at public peering?
So far, we're only looking at public peering. We haven't been able to figure out how to incorporate private network interconnection so far.
Yeah, that's a difficult question.
Yeah.
Thank you.